Hello everyone, this is Professor He. Nice to see you again. The topic of this task is about the saturated water vapor. There are many practical situations where two phases of a pure substance coexist in equilibrium. Water exists as a mixture of fluid and vapor in the boiler and the condenser of a steam power plant. The refrigerant turns from liquid to vapor in the freezer of a refrigerator. As a familiar substance, water is used to demonstrate the basic principles involved. Remember, however, that all pure substances exhibit the same general behavior. Remembering that any equation with two independent variables in the form z equals z xy represents a surface in space, we can represent the PVT behavior of a substance as a surface in space as shown in the figure. Here, T and V may be viewed as independent variables and P as dependent variables. This figure shows the PT diagram of a pure substance. This diagram is often called the phase diagram since all three phases are separated from each other by three lines. The sublimation line separates the solid and vapor regions. The vaporization line separates the liquid and vapor regions, and the melting line separates the solid and liquid regions. These three lines meet at the triple point where all three phases coexist in equilibrium. The vaporization line ends at the critical point because no distinction can be made between liquid and vapor phases above the critical point. Substances that expand and contract unfrozen differ only in the melting line and the PT diagram. Water expands unfrozen. Consider a piston cylinder device containing liquid water at 20 degrees centigrade and 180 atm pressure. Under these conditions, water exists in the liquid phase, and it is called a compressed liquid or a subcooled liquid, meaning that it is not about to vaporize. Heat is now transferred to the water until its temperature rises to, say, 40 degrees centigrade. As the temperature rises, the liquid water expands slightly, and so its specific volume increases. To accommodate this expansion, the piston moves up slightly. The pressure in the cylinder remains constant at 180 atm during this process, since it depends on the outside barometric pressure and the weight of the piston, both of which are constant. Water is still a compressed liquid at this state, since it has not started to vaporize. As more heat is transferred, the temperature keeps rising until it reaches 100 degrees centigrade. At this point, water is still a liquid, but any heat addition will cause some of the liquid to vaporize. That is, a phase change process from liquid to vapor is about to take place. A liquid that is about to vaporize is called a saturated liquid. Therefore, state 2 is a saturated liquid state. Once boiling starts, the temperature stops rising until the liquid is completely vaporized. That is, the temperature will remain constant during the entire phase change process if the pressure is held constant. This can easily be verified by placing a thermometer into boiling pure water on top of a stove. At sea level, the thermometer will always read 100 degrees centigrade. If the pan is uncovered or covered with a light lid. During a boiling process, the only change we will observe is a large increase in the volume and a steady decline in the liquid level as a result of more liquid turning to vapor. Midway about the vaporization line, the cylinder contains equal amounts of liquid and vapor. As we continue transferring heat, the vaporization process continues until the last drop of liquid is vaporized. At this point, the entire cylinder is filled with vapor, that is, on the borderline of the liquid phase. Any heat loss from this vapor will cause some of the vapor to condense. A vapor that is about to condense is called a saturated vapor. Therefore, state 4 is a saturated vapor state. A substance at states between 2 and 4 is referred to as a saturated liquid-vapor mixture, since the liquid and vapor phases coexist in equilibrium at these states. Once the phase change process is completed, we are back to a single phase region again, and further transfer of heat results in an increase in both the temperature and the specific volume. At state 5, the temperature of the vapor is, let's say, 300 degrees centigrade, and if we transfer some heat from the vapor, the temperature may drop somewhat, but no condensation will take place as long as the temperature remains above 100 degrees centigrade. A vapor that is not about to condense is called a superheated vapor. Therefore, water at state 5 is a superheated vapor. This constant pressure phase change process is illustrated on a TV diagram in figure 6.5. If the entire process described here is reversed by cooling the water while maintaining the pressure at the same value, the water will go back to state 1, retracting the same path, and in so doing, the amount of heat released will exactly match the amount of heat added during the heating process. It takes a large amount of energy to melt a solid or vaporize a liquid. The amount of energy absorbed or released during a phase change process is called the latent heat. More specifically, the amount of energy absorbed during melting is called the latent heat of fusion and is equivalent to the amount of energy released during frozen. Similarly, the amount of energy absorbed during vaporization is called the latent heat of vaporization and is equivalent to the energy released during condensation. The magnitudes of the latent heats depend on the temperature or pressure at which the phase change occurs. At 1 atm pressure, the latent heat of fusion of water is 333.7 kilojoule per kilogram, and the latent heat of vaporization is 2256.5 kilojoule per kilogram. The phase change process of water at 1 atm pressure was described in detail and plotted on a TV diagram. Now we repeat this process at different pressures to develop the TV diagram. Let's add weights on top of the piston until the pressure inside the cylinder reaches 1 megapascal. At this pressure, water has a somewhat smaller specific volume than it does at 1 atm pressure. As heat is transferred to the water at this new pressure, the process follows a path that looks very much like the process path at 1 atm pressure as shown in the right figure. But there are some noticeable differences. First, water starts boiling at a much higher temperature at this pressure. Second, the specific volume of the saturated liquid is larger, and the specific volume of the saturated vapor is smaller than the corresponding values at 1 atm pressure. That is, the horizontal line that connects the saturated liquid and saturated vapor states is much shorter. As the pressure is increased further, this saturation line continues to shrink, and it becomes a point when the pressure reaches 22.06 megapascal for the case of water. This point is called the critical point, and it is defined as the point at which the saturated liquid and saturated vapor states are identical. Okay, that's all for this task. Thank you very much, and see you next time.